Hello friends, been quite a while that we met last time. I've been kind of busy with a few things. Good news is that we have crossed 500 subscribers. Good news for me actually, at least, not for everyone. And I would like to thank everyone who has subscribed to my channel. And I believe you are one of the best people on earth. Basically because I have never actually asked anyone to subscribe. Secondly, all the material is available anyway. So if you subscribe, if you clicked that button, you did it on your own volition to just support me out, and I really appreciate that quality, and I really appreciate all of you for doing that. So as you can see, we are now starting with non-terrestrial networks this time. So I intend to keep it as a series of videos that will prepare you for a transition from terrestrial networks in 5G to non-terrestrial networks in 5G. And I believe it's a very good time to start this because till now you have to understand that even though technology moved parallelly for both terrestrial networks as well as non-terrestrial networks, but they had always been different technologies. They were moving on the same lines, they had similar interests that they served and everything, they had similar objectives, but they moved parallelly. If this was terrestrial, this was non-terrestrial based on similar principles, but they were quite different. So first time it is happening in the history of telecommunications that we are moving towards a merge. We are getting same set of specifications that will work for both technical and non-technical specification, and that is happening right now. It's starting with the release 17 of NR5G, and from there on in, the specifications and the development that will move hand in hand for both terrestrial network and non-terrestrial network, which we used to call satellite communications till now. That was a more popular term, but now NTN, non-terrestrial networks, is catching pace. So we'll study today, we'll start with it, and we'll see how we can adapt to that non-terrestrial networks. So today's topic will be timing adjustment or timing advance, you can say, and we'll have a small idea about how it happens in TN, what challenge NTN has posed, and how do we encounter that challenge in non-terrestrial network. Okay, fine with everyone? You all get it? What we are trying to do here? Okay, so first thing first, what is timing adjustment in current systems? Like we have terrestrial systems, let's say. What is timing adjustment in that? Okay, I'll give a very simple diagram, a general idea, and then I'll tell you how we encounter that. So that should help you out. And any questions, just ask me. So we work in a wireless system. Wireless system has a base station. Base station sends out packets called downlink packets. Everybody knows that. There's a UE somewhere. This is the UE. If it starts sending packet there, packet should take some time to reach here. And we all know that we work in telecommunications based on slot indications. Slot boundaries are there in time, and during that boundary everything has to be done. Okay, so if I say that this line represents time, this axis represents time, this one, then it represents time moving forwards. Then let's say if G node P is DL and UL, G node P are base stations, DL and UL are synchronized, they appear at the same time, okay, for slot N, then can anybody tell me where will UE's downlink slot N lie? Downlink only. Where will UE's downlink slot N lie? Will it lie right here only? Will it lie on the right side of it or the left side of it? On GNB. One vote is for on GNB, the other one is for right side. Okay, my vote is also right side. Reason being, let's say somewhere here, DL of UE. will lie for the same slot. The reason being, when packet is sent out here, it's sent out in this boundary, it will take some time to reach UE, some time, while it's propagating, and that is why it's called propagation delay. So it will reach UE here, after taking some time it will reach UE here, and that will mark at UE the start of the slot when it reaches. So if slot boundary here at GNB is this, let's say from here to here, then from UE it will be here to here, something like this, not exactly but something like this. So you understand how propagation delay comes in picture for the DL. Now can somebody tell me where will the UL of UE be? Will it be left side or will it be on the same or something else?
Right.
On the right side. My vote is for the left. Okay? I'm very glad that you're the best part is to correct someone's understanding, so that that's the learning, right?
Yeah.
Okay. So why? I will tell you. See, propagation delay will happen both sides, here to here and here to here, right? Now I'm saying GNB is the master. GNB says that at this time my downlink starts. So sorry, at this time my downlink starts. So after some time UE will reach and UE's downlink will start. Similarly, if this is the delay, if this much delay is there already, that much delay will also be there in uplink. So if UE starts sending out a message, that should ideally take same time, same amount of time, right? So to counter that, UE must start its uplink here, then only it will reach at the correct time at GNB. Is it clear?
Yes.
Have I made myself clear?
Yes.
Now there are two more problems. Do you understand why UE has to start earlier for uplink?
Yes.
It's due to propagation delay. Now there are two more issues that we encounter and correct using the same procedure known as timing advance in terrestrial networks as well. So UE is here. This is, let's say, the cell. So this UE is here. Do you agree with me when I say if a UE is here, more close to the base station, its delta will be different because its propagation delay will be different. Downlink will reach earlier and uplink, it will have to start later than this one because it will take less time to reach. Now G node P starts its processing in a batch. It doesn't start processing uplinks differently for each UE. So all the packets, all the UE packets in UL have to arrive synchronously at the same time, right? So every UE will have to apply different timing advance. Okay, so this is one problem that we this is a geographical problem, geological problem, where in the geography the UE is located. Second issue is the issue of mobility. Now if I say it is the same UE, it was here earlier but later on it moved away from the cell, then its timing adjustment must also change, right? And how do we get to know that? So for that we have timing advance procedure. That procedure is based on an idea that if this is the frame boundary, slot boundary at G node B, then packet must arrive like this, completely fitting. But we also have a concept of guard period. So the packet completely is not like this, packet has guard period at the end. So this is the packet, let's say, this is the guard period, and if it arrives like this, then packet is still saved, okay? It's still saved, it's still workable, but we know that this much delta is to be corrected. This may have happened because of mobility, okay? So G node B will calculate this much delta, and based on that it will provide a MAC control element message known as timing advance tag. That value you will receive and you will be like, okay, my timing adjustment is not 100% correct at this moment and I need to apply that. and once I apply that, the packet will start fitting in like this. So it's an ever going process. Okay, so that is how timings are corrected. So everybody is okay with this?
Yes.
This is TN. I'll give you a few calculations based on which UE applies. There is one detailed video I already have about TA on NTN which explains this procedure, how TA comes, and how all the timers, TAT, timing alignment timer, TA maxi, I discuss all these things there. Here I will skip those, but I will give you an equation because that equation is an important one. So once we receive timing advance UE, once UE receives the timing advance from G node B, it receives a value called TA. We call that value TA. Okay, we also call it TAC sometimes. Once it receives TA, based on TA it calculates NTA. What does it calculate? It calculates NTA. NTA is nothing but very simple equation. TA is not a good one. TA and let me cheat, into 16 into 64 by 2 to the power numerology. Okay, we calculate NTA. Okay, so this is calculated every time TA comes. So we already have a NTA value maintained because it's coming regularly, right? So we calculate a new NTA now. This is new NTA, right? No, this is just NTA. Okay, this is calculated, and then we calculate from NTA, we calculate TTA. There is another calculation known as TTA, and TTA is governed by this. This is going to be a very important one. NTA and plus NT offset. This is a value, and TC into TC. NTA is what we calculate like this. There is one equation I'm a little bit confused about. You can check on yourself. So NTA keeps updating. We have an old NTA, and then from that NTA and this TA we can calculate a new NTA. Okay, I think for the first time we use this one. For other times when we have for the first time we won't have any NTA old, but when we have NTA old, then we use that equation to calculate this NTA. We put this NTA here. This is a constant that has been received from system information. Okay, and TC is the unit of time in NR5G. So based on that we calculate TTA. This is the exact actual timing advance value. Is that okay? Remember this. This is going to be very important when we move on to NTN. Fine. To give you a better picture about timing advance, I'll show one more picture because that will be very important later on. Okay, so at GNB, this is DL. No, this is not DL. At GNB, this is DL. Okay, this is slot N. This is N plus 1 and so on. So this is DL at G node B. Fine. Okay, G node B does not want to process at the antenna level. It doesn't want to do transmission and receiving at the same time. So it itself maintains a small, very small delta at G node B. Very small. It's much smaller than the slot boundary itself. Like it will be very small, like this. Picture is not good. Something like this. This small thing is called delta. This is being compensated with NTA offset. Okay, and at UE this will reach a little later. Okay, let's say it will take this much time. Okay, it is taking this much time. and this was UL GNB. It is taking this much time, so we will have to compensate this. This is propagation delay, this an offset delay at GNB. So this delay here we have to offset. So here we should be starting the uplink of UE, and this is downlink of UE. So this is timing adjustment. Is this understood? Am I making myself clear?
Yes.
Cool. Now we move on to the world of NTN. Should not have rubbed that off. Okay. Problem with NTN. First up, सबसे पहले objective. We need to know the objective, why we are doing anything, and to understand the objective, we need to know the problem. What is the problem, right? So as you could see, there was a base station and there was a UE and there was a line of sight signal. Not so much anymore. In case of NTN, there is going to be a satellite and there is going to be a gateway, and the G node B could be co-located, could be not, but let's say gateway is here and G node B is here. This additional delay has been added. This additional delay has been added, and this will cause so many problems, myriad of problems, and we are here to correct it. Okay, that is the objective, that is the sole objective. How do we do? So if we do only terrestrial part, if we do only NTA based calculation, that is not sufficient, because NTA cannot correct this big of timing adjustments. It just simply cannot. And even if we try to do it, here satellite is also mobile, so it is also it's also moving, and it's also need to be compensated. It's also posing another problem with respect to timing advance. Secondly, signaling overhead will be too high if we simply depend on that TN philosophy, because it will be needed very frequently, because satellite is also again moving. Okay, signaling overhead will be there. We will need more information because there will be big timing delay, so big timing advances will be needed. Big, like in terrestrial network they are in terms of microseconds, but here there will be in terms of multiples of milliseconds. So that's a big difference. So we'll be needing huge data over the air, huge signaling data over the air, so that will impact the throughput and bit rates. So that is not suggested, that is not practically possible. So UE shell has to support the pre-compensation in such cases. So in this case we have done few things and we'll try to address them. So first of all, there are these two delays that has been added. We can classify these two differently. First up, we can call that this, whenever satellite will move, it will not have any impact on other UEs based on this particular path. This is called, by the way, feeder link, and this is called service link. So whatever is happening on feeder link, is it common to all the UEs? Whatever is happening on feeder link is happening between satellite and base station gateway. Is it common to all the UEs?
Yes.
It is common to all the UEs, right? So any timing advance, if we need to correct on this, any variability, if we need to correct on this, we can call it TA. Let's say we call it TA common on feeder link, and on this one it may have multiple UEs being served. This one we can call TA UE. You understand that? That part. This is additional. Okay, this part is additional. So there is a there is a concept that has been thought out and said that simply you do nothing much, nothing ultra fancy, but you calculate TTA now using this. TTA now using this. NTA, we were doing it before, right?
Yes.
Plus NTA offset, we were doing it before, right? And plus now it says do an NTA adjustment commonly, so this brings in feeder link, and do an NTA adjustment on a UE into TC. That is all. This is it. Timing adjustment over. That's all you have to do in RRC connected state at UE side. On UE side, you don't have to do anything else. Finished. How do we do this? How do we do this calculation, and how is it made easy for us through the GNB to do that? Okay. So there are ideas for each of them. So NTA UE, this particular part, for the calculation of this, specifications don't specify anything. They don't specify how UE will do that. UE will autonomously do that, but network will provide some things that will help UE. Okay, that will help UE. What will they provide? They will provide something called ephemeris info. Ephemeris info. Okay, what is ephemeris info? Ephemeris info is information about the satellite. Okay, how, where the satellite actually is, with what velocity satellite is moving, and since I'm calling velocity not speed, so the vector also, in which direction satellite is moving. Based on all those information and UE's own location, UE should be able to calculate the adjustment or the propagation delay that will take place on service link, and UE should be able to pre-compensate that using this particular equation. Okay, first part done.
Yes.
On a top level done. Okay, not easy, but yeah, on a top level done. Secondly, NTA common is to be for now you assume that this whole path feeder link is to be adjusted at common, but that's not true. It's not happening exactly like that, but for now let's assume that feeder link is to be compensated by UE based on TA common. For TA common we have NTA common, and for NTA common calculation we have some value that is being provided by network, like 4 parameters I'll name here: TA common drift, TA common drift variation, and T epoch time. These 4 values will be provided by network. If they are not provided, then we will take NTA common adjustment as simply 0. Okay. Based on that, there is a calculation which is like this. Okay. Let me like this: delay common T equals, I said TA common, right, by 2, and plus TA common drift by 2, and into T minus T epoch. And TA drift variant by 2, TA drift variant by 2 into T minus T epoch square. Don't worry if you can see the equation correctly, you can find it anytime. Based on this, we can at time T we can calculate the delay, and NTA common would be nothing but same delay for DL as well as UL. So delay for DL at N and delay for UL at N, something like that. So based on that, you will calculate. Now the question, I have constantly said that this simple equation, these simple calculations and timing adjustment done. Okay, but where would we get these? TA drift and everything and the ephemeris info and all. So there are actually a lot of challenges with respect to that, and the challenges are that this information changes very frequently. This information changes very fast. Ephemeris will change very soon, frequently, and other things will change very frequently soon. And if you are familiar with the 5G specifications, what does happen when system information changes? When system information changes, there is a procedure called SI modification. So at SI modification, a flag has to be set, and the value tags are to be sent in SIP1, and that is a very expensive procedure, because this first if any SIP changes, we have to send the SIP1 with value tag, and we have to do SI modification through paging, etc. And then UE shall have to collect all the system information again right from the start, and that is a very expensive operation if this information will trigger that. Okay, so to ensure that doesn't happen, SIP19 information, this information has been kept out of that particular procedure, so it will not trigger a change in SI modification or value tag in SIP1. This will not. Okay, so this is another thing that you need to know. And now the point of UTSRP. Okay, why UTSRP is very important, and this point I have discussed with many people. They don't seem to know why do we need it at all. So the thing is, I told you this is satellite, and this is UE, and this is gateway. This is gateway. This is feeder link. This is service link. This is additional UE adjustment delay. Okay. So I told you this is done with NTA UE adjustment, and I recently told you this common TA ADJ. This is based on ephemeris info. UE will do self-estimation and pre-compensate it using that big equation: NTA offset, NTA UE adjustment, NTA common adjustment, NTA UE adjustment. I told you that for service link. I stand by it still. Okay. But I also told you that NTA common adjustment UE will do again based on satellite and gateway based on common parameters, because this part is common to all. Okay, this is because of satellites movement and common to all. So this will be done based on common parameters supplied by network, but compensation calculation to be done by UE. UE will pre-compensate the timing advance. Fine? Everybody cool with that?
Yes.
Okay. So problem is that based on the common parameters, TA common drift and everything, and based on the satellite ephemeris info, a smart person sitting here shall be able to triangulate the position of gateway. With all that information, we know where the satellite is, we know how it's moving, and we know the common drift and whatever it's using to compensate this particular delay. Based on that information, a smart person, good, nice mathematical person, the kind of scientists you see being captured by terrorists in Hollywood movies, they will be able to figure out the location of gateway, which we don't want. Satellite gateways can be very khufiya places. What's khufiya in Angrezi?
Secret.
Secretive places. So they can be. So we don't want that. So another, another concept arose, and that concept is called duty SRP, wherein we provide a point here. We call it UT SRP. Uplink time synchronization reference point. So UT SRP, now NTA common is only to be calculated over UTSRP. UTSRP, where does it lie? It can lie on satellite, it can lie on gateway, it can lie anywhere on feeder link. So between these 2 points, it can be anywhere. And UE will correct its timing advance only on this particular path now. Only up to this. This NTA UE adjustment, this NTA common adjustment. Fine. This part UE will not correct anymore. But again, timing will be affected by this part also. Understand? It will. There is no two ways about it. Then how do we correct this one? Now we shall revisit the timing advance again, and I'll show you how we do this. So initially, when timing advance was being considered, it was under discussion. Before specs were frozen, multiple things were considered. You remember this picture? This is this is GNP-DL. Okay, G node P DL. This is GNP-UL. For now, let's consider that they are same place. We don't consider delta now. Okay, for now. Okay. Terrestrials usually used to work like that. Now this is UE-DL. So this must be UE-UL. This propagation delay, same. Understood? Now consider heavy propagation delays. Heavy, like NTN. Where will UE-DL be lie comparatively? Very, very far comparatively. Let's say here. This have large implications because now UL has to start here. Understood? How much timing adjustment that is? This large value. Large value frequently over the air means heavy signaling overhead. And not only that, this poses another problem. If I receive N here at UE, uplink would already be, let's say, N plus K working on, where K is very large value. Now if we receive DCI here, and DCI is a command, let's say it's an uplink DCI, so it's a command that you will have to send uplink data. Okay, in that uplink data there is a something called K value, K2 will ask that after N plus K2 value you send the data. K2 value here will be too large also again, and it will be very difficult to manage. Earlier when N was here and N was here, K2 would be 4, so N plus 4 you can send because not that propagation delay, but here it could be like N plus 24, N plus 50. So by the time G node be sent the ULDCI, the data shall be coming after a heavy amount of time. So that increases what? Round trip time a lot also. Propagation delay and also adds up round. So those are different problems. If we don't add the round trip time delay, then these K2 values should be large. To encode them again, we will need more bits, more signaling overhead on the air. So one suggestion was that to overcome this, at the UE side we wanted less At the UE side, we wanted less adjustment, small timing adjustment. We don't want to send TAC in Mac CE, big values every time. So another suggestion was that this is G node B DL. Then we keep G node B UL here. What purpose does it serve? Let's say here UE received N DL. Okay, this is the timing advance.
Yeah.
So here also it needs to send somewhere here uplink, right? And now you can see the timing delay is small at UE side. You understand what I'm trying to say? Okay, so this solves that signaling overhead problem. Fine. This particular thing, this offset at GNB and DL, this particular offset is being driven by a variable called Kmac that we'll study later on. Kmac becomes very, very, very important in timing relationships. Like the one relationship I just told you, that for N, you send uplink data at N plus K2, right? That was terrestrial. Now here, Kmac plays a very big role in the starting of timers when a particular timer is to be start. For example, RARSP window timer, Kmac has a role there. And you know, other timing relationships, basically it has not timing adjustment, don't confuse these two, timing relationships, slot relationships. If something is coming at N, at what slot I send it. Okay, so in that Kmac does a very big role. Now why I told you this right away is, let's get back to this. If satellite is here, if UE is here, if gateway is here, and this is feeder link, and UTSRP is there, then this particular adjustment in timing, if timing is getting little bit bad at here, then what will happen? It will happen to all the UEs. All the UEs will be like that their uplink is reaching here rather than here. Then what can G node B do to assist that? G node B can push its slot and completely here, all of it. Problem solved, because all UEs were having same problem. So what it did, it changed its Kmac dynamically. So using this Kmac value, G node B compensates timing advance here between gateway and UTSRP, uplink timing synchronization reference point. Okay, so Kmac plays a role here. In short, if I were to give you a gist, what was NTA timing adjustment problem and how have we encountered it, I believe if you go through this particular video, you will have to go through this particular video multiple times. If you are new to this, you'll go through this video a few times, and then you learn from specifications or other sources, you will understand it very well that the problem was extra timing delay. How solved? NTA offset के साथ two new things. This calculated based on ephemeris info.
Yes.
Ephemeris info provided in SIM 19, but does not trigger SI modification. This problem solved for feeder link up to only UTSRP. Since it's common to all UE, common variables are provided. SIM 19, based on that compensate this. This part is remaining, compensated using Kmac via G node B. Why? Why not keep it here and let the UEs do that? Triangulation problem. Base station is secretive. We don't want it to be found. What else? Did we study anything else? That's it. That's a very small timing adjustment part that has been adapted into 3GPP specifications to counter the problem of timing adjustment while not touching the terrestrial adjustment. So, any doubts? You can ask now, you can come to me later, but I hope you have a good time understanding this concept. Very important concept, very basic concept. The first problem the NTN ever faced while transitioning from terrestrial to NTN. Very simple, very basic problem, and I must say has been actually dealt with very marvelously. It's very intelligent solution. So that's all I have for you all today. Let's meet soon again.